So in the last module, we have seen examples of Markov chains after having defined Markov chains. But now it's time to get back to general Markov chains. So what we'll do here is basically start with listing some basic properties that arise from the definition, set up the notations, basic notations, etc., etc., and then introduce initial distribution and calculate other distributions. An important thing would be bringing the matrix notation, and then at the end what we'll do is we'll analyze in detail a particular Markov chain, namely on and off chain, which has been already, we have given an example of that. So we'll analyze that in detail to basically see some of the interesting properties that we could be investigating for a general Markov chain, mainly the long-term properties. Now we are about to get into the general, so having seen some examples, we want to get into the general, some preliminaries of Markov chain, preliminary facts about Markov chains. But as I said, Markov chains, a lot of manipulation and everything regarding Markov chains depends really, clever use of conditional probabilities and so on. So I want to quickly recall some basic results in conditional probability. These are all results that either you know or you can directly derive these things by using the simple definition of conditional probabilities. So I'll just list them: CP1, CP2, CP3, CP4, CP5. CP5 is sometimes called the theorem of total probability. And then CP6, which is kind of a generalization or extension of CP5. CP5 is for the formula for the unconditional probability of B, broken up as weighted sum of conditional probabilities. CP6 is something analogous, but now we want to write the conditional probability of B given C as a weighted sum. So these properties would be used left and right in the analysis of Markov chains. Okay, so back to Markov chains. We've seen enough examples. We'll come back to the examples again, but let's now do make some basic observations about Markov chains. So suppose Xn be a Markov chain. Sometimes I'll abbreviate Markov chain as an MC, state space S and transition probabilities Pxy for xy in S. Recall that Pxy represents the conditional probability that the chain will move to state y at the next time point, given that the present state is x. Now it's a natural question to ask, what about probability of moving to a state y after two steps? Because Pxy gives the probability of moving from x to y in the very next step. What if we are interested in the probability of moving to a state y not in the immediate next step, but after two steps? That is what we are asking. Okay? These are often called two-step transition probabilities. Again, it's what you are going to see are very basic computations with conditional probabilities. So as I mentioned, using CP6 and CP3 and the Markov property, so you can easily see that the conditional probability that we are interested in can be broken up as the sum over all z in S. That's the first step. Then you use CP3 to write that conditional, each of these summands in this fashion, and then using very definition of Markov property or Markov chain, you can see the first factor in the summand is nothing but Pxz, because you are asking for the conditional probability that xn plus 2 is y, given the entire history up to n and n plus 1, and you are given that xn plus 1 is z. From the definition of Markov chain, we know that that conditional probability is simply Pxz, that is the probability of transition from state z to state y from time n plus 1 to time n plus 2. And similarly, the second factor becomes Pzy. So the two-step transition probabilities that we are interested in turned out to be this, But the important thing to note here is that, so this particular quantity that we have obtained is denoted by Pxy super bracket 2. We put bracket 2 and not just 2 to avoid confusing this as Pxy square. And this is called a two-step transition probability from state to state x to state y. Now remember what we have just proved, namely this fact. We started with the conditional probability that xn plus 2 equal to y given the entire history up to x, but at the end the expression that we got, if you look at it closely, you will see that it is Pxz into Pzy summed over z in S, which means ultimately it depends only on x and y and not even on n. So that is what is basically captured in this last equality. So what we have proved actually gives us this. So this time homogeneous Markov property retains even when we consider two-step transitions. Now in a similar manner you can talk about k-step transition probabilities, and I'll just quickly show you the results. So P super bracket k xy, that's the ultimate expression, and that can be written as Pxz super k minus 1 Pzy, or the other way around, but it ultimately turns out to be the sum Pxx_z1 Pzk minus 1 y, where this last sum is taken over all possible k minus 1 tuples z1, z2, zk minus 1 in S. So these are what are called k-step transition probabilities. Now there is an interesting thing. It turns out that in Markov chain theory, using matrix notation makes often things very convenient to write and also elegant. So I'll just introduce that idea. So firstly, transition matrix. So we have these transition probabilities Pxy for a Markov chain. Consider this S cross S matrix, which I call P, which is, well, S cross S I actually mean, it's an abuse of notation. What I actually mean is the cardinality of S is the order of the square matrix, and the xyth entry of that matrix is Pxy. So it has S many rows and S many columns. So number of rows and number of columns you see is a number of states, and the xth row yth column element is Pxy. So this P is often called the transition matrix or sometimes called transition probability matrix. Now property 1 of the transition probability said that Pxy's are all non-negative, and in terms of the transition matrix it says that all the entries of the matrix are non-negative. And the second property of the transition probabilities was, for every fixed x, if you sum Pxy's over all y in S, the sum is 1. Now in terms of the matrix, it simply says that this matrix, each row sum equals 1. Next, if you look at the formula for Pxy2, which is the two-step transition probability that we obtained, the formula was Pxz into Pzy, that product, summed over all possible z. But your knowledge of matrix algebra would tell you that if you look at the matrix P and then look at the square of the matrix in the sense of matrix multiplication, then this quantity Pxz Pzy summed over all z is nothing but the xyth entry of the P square. So which means if we look at the square of the matrix P, then its entries really give us the two-step transition probabilities. So that's very convenient, and that's generally true for kth power of P represents really the matrix whose xyth entry really gives the k-step transition probabilities. Well, this is for all k greater than or equal to 1. For k equal to 1, Pxy1 one-step transition probability is nothing but Pxy. Just to complete the picture, we can write it for k equal to 0 also, where Pxy0 is zero-step transition probability, which is of course delta xy, which as you all know stands for delta xy is 1 or 0 according as x equals y or x not equal to y. and of course P to the 0 is identity matrix. So everything matches up. We now go to a very important result of Markov chain theory, which is called Chapman-Kolmogorov equations. Actually, look at the trivial identity of matrix powers, and then if you identify the xyth row of the left hand side and equate it with the xyth row of the right hand side, that product of p to the m and p to the n, you trivially get this equality, this identity. Now, this identity is very, very well celebrated, known as the Chapman-Kolmogorov equations, sometimes abbreviated as CK equations. Of course, we see this as an immediate consequence of this matrix algebra. However, if you look at this, free of this matrix notation, etc., you can also try to give a probabilistic interpretation to this. Basically, see that on the left hand side you are looking at the transition probability of going from x to y in m plus n many steps. Obviously, in order for that to happen, what you need to do is go from x to some state z in m steps and then follow it up by transition in n steps from z to y. Of course, it has to be summed over all z in s. So it also probabilistically looks fine. You could have proved it directly, but all we wanted to see is how easily it follows as a consequence of adopting this matrix notation. Okay, now we introduce two very, very important notations which is going to remain with us throughout the analysis of Markov chains. For any event A involving the sequence xn, we denote P sub xa to be the conditional probability of the event A given x not equal to x. So it's basically conditional probability of an event A for the Markov chain conditioned on the chain starting at x. Similarly, we talk about conditional expectation for any real random variable determined by the Markov chain xn. E sub x z is the conditional expectation of z given x0 equal to x. So essentially, this is what is explained here. For each x in the state space S, Px denotes the conditional probability and Ex denotes the conditional expectation given that the chain starts at state x. So these are very handy notations for this conditional probability. Now, clearly with this notation, what we call Pxy can be easily written as P sub x x1 equal to y. Also, of course, probability of an event, conditional or unconditional, is the same as expectation of the indicator of that event, and that's what is written in the next. Second one is for the analogous one for case tip. Now, here are some facts which I leave as exercises. You should try these exercises. Basically, using Markov property and also time homogeneity, one can show all these things. So I want you to treat these as exercises. So this is the first one. Talks about given the past history up to time n and given that at present time n you are next, the conditional probability of successively moving from x to y1, then to y2, then to yk in the next k many steps. That probability is simply given at the end by the product of the transition probabilities, which is the extreme right hand side of this identity. And here for any b in s to the k, look at the event that xn plus 1 etc. xn plus k, this k tuple belongs to the set b. That's an event determined by the k many steps after time n. You want the conditional probability that that event given the past history up to time n and the present state is x. One can easily show by using Markov property, just writing down this conditional probability. You can show that it's this. And similarly for any function on sk to r, if you look at this random variable f of xn plus 1 etc. xn plus k, so it's a random variable that depends on the next k states of the Markov chain after time n. So the conditional probability, a conditional expectation of that, given the past history up to time n, it is just as if you started the Markov chain at x and ask it, what's the expectation of f x1, x2, xk. Of course, in the previous two things, we looked at an event depending on the next k random variables after time n, and a random variable depending on next k random variables, next k states after time n. So these are dealing with finite futures, xn plus 1, xn plus 2, xn plus k. But similar things hold for infinite future as well, which is embodied or captured in these results. It's not so difficult to show, but not as easy as for the finite history or the finite future. Okay, anyway, the upshot of all this is that given the past history up to a time n and the present state x, the future conditional evolution of the chain is exactly, it's not just one step or two step. The entire evolution of the chain in the future, conditioned on the past up to time n, is exactly as if it's the original chain, except that it's conditioned to starting at x. And the corresponding conditional probabilities and expectations are all completely determined by the transition probabilities of the Markov chain. That part is clear. Now, so far we have been always talking about conditional probabilities, conditional expectations, etc., etc. And just now we have seen conditional probabilities and expectations related to future evolution. Given the history up to any time point, they reduce to p sub x, e sub x, etc., which in turn are determined by transition probabilities. But, we may be interested not always in conditional probabilities, but we may be interested in unconditional probabilities and expectations. So for that, what we need to do is, we need to specify the distribution of the initial state x0, and then use this simple result on unconditional probabilities or unconditional expectations as weighted sums of conditional probabilities and conditional expectations. So if we denote the distribution of x0 by, so it's clear that once you know the distribution of x0, then you can find those unconditional probabilities or unconditional expectations by that formula. If you denote the distribution of x0 by mu, by that I mean mu sub x is the probability that x0 equal to x. And if you write p sub mu and e sub mu respectively for the unconditional probabilities and expectations arising out of mu, then the above relations reduce to these relations. So ultimately our upshot is the distribution of the Markov chain is completely determined by initial distribution and the transition probability is this. But the point of all this is that, another point that you should not miss is that this last formula for p sub mu a and e sub mu z really tells you that at the end of the day it's enough to know what the pxa's and exz's are. Once you know how to compute those things, then given any mu, finding p mu a and a mu z is an immediate calculation based on this last written identity. So let's carry on with this a little bit. So for example, if you are given an initial distribution and transition probabilities, then one can write the joint distribution of x1, x2, xn in this fashion. So here initial distribution as well as transition probabilities are all given. In particular, you can also get the marginal distribution of xn, which is given by this formula. So if you denote the distribution of mu n, distribution of xn as mu super n, then the above formula says in matrix notation that this is what it is. Mu super n is mu times p to the n, where both mu and mu super n are viewed as row vectors, 1 cross s row vectors. Thus, essentially, probabilities of all finite dimensional events are explicitly given in terms of initial distribution mu and transition matrix p, which is what the last two identities do. But the important question for a Markov chain really centers around understanding its long-term characteristics. One is really interested in those things really, and somehow or other these long-term characteristics, understanding them, really involve infinite dimensional events. And unlike the finite dimensional events for which we have explicit formula in terms of initial distribution and transition matrix p, it's not so easy to get such explicit formula for infinite dimensional events, even though the probabilities are all determined by mu and transition matrix. But you don't have an explicit formula like in the finite dimensional cases. But the issue is, what are those questions that one is interested in? And in view of the difficulty that I have just raised, how does one answer them? Okay, now before we get to the question, let us again go back to a very simple example. And the reason for that is, this is the on-off chain. We have already given this chain as an example, seen this chain as an example. The reason I want to go back to this is a complete analysis of on-off chain, which is going to be possible explicitly, but it will help us identify at least one important question for general Markov chains. So let's quickly recall the on-off chain. State space is 0 or 1. They just really represent the off and the on states. The transition probabilities are as written there. P01 is alpha, and therefore P00 is 1 minus alpha. Similarly, P10 is beta, which means P11 is 1 minus beta. And let's assume that the initial distribution is given by mu0 and mu1. There is a probability of x0 being 0 or 1 is mu0 and mu1. Of course, mu1 is 1 minus mu0. And denote, as usual, mu0n to be the probability that xn is 0, and mu1n to be probability xn is 1, which of course is 1 minus mu0n. Then there is an easy recurrence relation between the successive mu0n's. Why is that so? That is because mu0n is mu0n minus 1 into p00 times mu1n minus 1 into p10. This you get easily by conditioning on xn minus 1 being 0 or 1. So it's basically an application of theorem of total probability. But then, using the fact that mu1 n minus 1 is 1 minus mu0 n minus 1, you can write the right hand side completely in terms of mu0 n minus 1. And if you do that, the second expression on the right is what you get, beta plus 1 minus alpha minus beta into that. So essentially what this does is, I have expressed mu0 n in terms of mu0 n minus 1. So that's what we meant by the recurrence between the successive mu0 n's. And now, of course, if you iterate this, by that I mean, in place of mu0 n plus 1, substitute its expression in terms of mu0 n minus 2 and carry on like this, then what you end up getting is this simple result. That's just algebra. Okay, that's what you get. So essentially what you are able to do is, you are able to write mu0 n completely in terms of mu0 by successively reducing from mu0 n in terms of mu0 n minus 1, then in terms of mu0 n minus 2, etc. If you keep on doing this, finally this is what you get. Now we have to simplify this. There is a sum, and you see that the sum is a finite sum of a geometric progression, 1 minus alpha minus beta to the power k equal to 1 to n minus 1, so that's a GP with common ratio 1 minus alpha minus beta to the k. Of course, if the common ratio is 1, then the sum we know what it is n minus 1. But when the common difference is not 1, then there is a nice formula. But for the common ratio to be not equal to 1, what we want is, we want alpha plus beta to be not 0. So that's what we assume. Remember, alpha and beta are probabilities. So alpha and beta are both non-negative. So we assume that alpha plus beta is strictly positive. It's clear that it simply rules out that both alpha and beta are equal to 0. And it's okay. And think about it, what it would mean if alpha and beta were equal to 0, to convince yourself that this is not such a big assumption, big restriction. Okay, so this tells you that 1 minus alpha minus beta is not 1, which means that you can now apply that formula for sum of geometric progression, and you get this one. And remember all the time, so this is a nice expression for mu0 n in terms of mu0. And of course, remember always that mu1 n is 1 minus mu0 n. Of course, at this stage, all three parameters, important parameters, mu0, alpha and beta are involved. Remember, these three parameters determine everything. Mu0 determines mu1, which means you know the initial distribution completely, and alpha and beta determine the transition probabilities also completely, all transition probabilities. So now the main question that we are going to ask, like we said that we are interested in the long-term behavior. So we ask, what if n goes to infinity? Is there a limit? If so, what is the limit? Now for that, you see that n is involved in one place only in the expression from mu0 to n, namely as a power of 1 minus alpha minus beta. So you're basically asking what happens to that power, nth power of 1 minus alpha minus beta as n goes to infinity. Of course, you know from calculus that in order to know that that has a limit, you need to have some condition on 1 minus alpha minus beta. So in order to get that, we already know that 1 minus alpha minus beta is positive. So now we assume that alpha plus beta is less than 2, strictly less than 2. Once again, alpha and beta cannot be more than 1. So it's always less than or equal to 2. And we assume that it's strictly less than 2. So it only rules out alpha equal to beta equal to 1. And once again, it's for you to convince yourself that, ask yourself what would have happened if alpha equal to 1 and also beta equal to 1. And convince yourself that therefore this ruling out that condition, ruling out that contingency is not such a restrictive assumption. So once you have these two conditions, namely alpha plus beta is positive and alpha plus beta is less than 2, both inequalities strict would tell you that 1 minus alpha minus beta in modulus is strict less than 1, and that's all you need. Then 1 minus alpha minus beta to the n, we all know goes to 0. And therefore we conclude that except in the case when either alpha and beta are both 0 or alpha and beta are both equal to 1, both of which are trivial cases, what we get is that except in those two very trivial cases, the limit mu0 n exists and is given by beta over alpha plus beta. Let's call it pi naught. And obviously mu1 n, which is 1 minus mu0 n, that limit would also exist and be 1 minus pi naught, which is alpha over alpha plus beta. So what are the main takeaways from this above analysis? Well, firstly, the chain has a unique limiting distribution. That is, probability xn equal to 0 converges to a limit, probability xn equal to 1 converges to a limit. The limit depends only on alpha and beta. Remember the expressions for the limits? We got beta over alpha plus beta for the limit of mu0 n and alpha over alpha plus beta for the limit of mu1 n. So the limit ultimately depends only on alpha and beta, and somehow surprisingly, the dependence on mu is gone. The initial distribution, that is gone. So this is not so surprising anyway, because as we will see later, initial distribution often has very little or no effect in the long run. Next, the limit distribution that we got, which is, we can call it pi, which is pi 0 is beta over alpha plus beta and pi 1 is alpha over alpha plus beta, has this another very interesting property. If I take this distribution as my initial distribution mu and then compute the distribution of xn, it turns out that mu n is also equal to pi, and that's true for every n. What it means is that if I take x0 to have distribution pi, then all the xn's would have the same distribution pi, when pi is this particular distribution. To do this, first prove pi p equal to pi, and I'm talking about proving that matrix equation, and then from that you can easily conclude that pi pn equal to pi over all n. Now this property is a very important property. This property is often expressed by saying that pi is a stationary distribution. Secondly, another very interesting observation is that this is the only stationary distribution. That is, this is the only probability on the two-point space 0, 1 space which satisfies pi p equal to pi. No other probability will satisfy this. So, here is a summary. The on-off chain has, irrespective of the initial distribution, a unique limiting distribution, which is also a stationary distribution for the chain and the only one. Of course, this naturally rests us with the questions, do same results hold for a general Markov chain? Well, most of you would probably expect that the answer is no. Now, if that is the situation, then the next natural question is how to go about understanding long-term behavior for a general Markov chain. Now remember, the distinct advantage for the on-off chain was that we could actually do a lot of explicit computations. We could actually get a simple explicit formula, closed form expression for mu n, from which we could then perform the limit as n goes to infinity. Unfortunately, and quite expectedly, such explicit computation would not be possible for general Markov chain, which means that we'll have to employ ideas that do not depend on such explicit computations. So I would say that the main takeaway at this point of time would be, apart from all the notations, etc., that we've already established, the important thing is that we have analyzed the very simple two-state chain, namely on and off chain, completely. In particular, we have seen it has a limiting distribution, which turns out to be a unique stationary distribution, etc. So now our focus would be try and go through same kind of analysis, of course, without being able to do such explicit computations for general Markov chains.